In this lesson, we're going to learn about delayed load workflows and packed primitives. Let's start with some slides. It's one thing to be able to render a scene, and it's another thing to be able to render that scene efficiently. Effects is often to do with natural phenomena, and they tend to be very, very complex and detailed. Lots and lots of kind of fractal detail, lots of tiny forms within forms. And that tends to require a lot of geometry in order to represent it. If we can handle that geometry more efficiently, then we can squeeze in more detail and we can squeeze in more iterations. So if we can render something in an hour that would normally take overnight, then we might be able to get a couple of iterations done during the day. And the more iterations we can do, the more feedback we can get. Creative feedback is absolutely crucial to producing high quality visual effects. It results in better looking work. And one place we can gain efficiency when it comes to rendering is in the geometry pipeline. So let's look at the traditional effects rendering pipeline. So in the old days, you would load assets as Houdini geometry, so points and faces. You'd use that to set up simulations, and you'd run those sims. Then you'd cache them out to disk. This would still be as native Houdini geometry, so BGO or some of the older formats that Houdini used to use. And then the ROP, the render operator, would write a description of this scene into an IFD. So it'd be loading up that cache geometry and then writing it into an IFD. And then when you went to render it, Mantra would read the data from that IFD in order to render the image. It would look a little bit like this. So going from left to right, you can see the asset being loaded into Houdini to set up a sim. Then the sim would be cached, and then Houdini would read it back out of the cache, and then the ROP would write that into an IFD file. IFD stands for instantaneous frame description, by the way. And then finally, Mantra would be reading that IFD file off disk again in order to render the image. So there's quite a lot of reading and writing going on there. And there are a few disadvantages to all of this. The cache data gets written to disk and then read again during the IFD generation process, and then written into the IFD file. And then finally it's read from disk again by Mantra. All this reading and writing takes a lot of disk space and time. And it also takes a lot of network load. If you work somewhere where you're not saving all of your data on your local disk, for example, most visual effects studios, then that puts a lot of strain on the network, reading and writing all of that data. Generating the IFD file takes a long time, as Houdini's writing all the data into it. So when you actually go to submit a render, it takes a while because Houdini has to write a lot of data to disk. I already mentioned the network load issue. And then Mantra can't start rendering until it's read all of the data out of the IFD. So it takes a little while before you can start seeing a render. Let's look at a delayed load rendering workflow, which is the ideal way to do things now. So you load assets. Ideally, they would be in some sort of packed format, like an Alembic. You would set up simulations as before using the assets. If the assets can remain packed during the sim, if it's something like an RBD sim, then that's ideal. Then the simulations would be cached to disk, and this time the ROP would, when it's writing its scene description into the IFD, it writes references to the cache data on disk. It never actually writes that data into the IFD directly, it just writes references to it. Then Mantra reads that IFD file, and when it gets to the bounding box of an object that needs that data, it loads the file from disk. And this looks a little bit like this. Again, on the left, it's pretty similar. We load the asset, we set up our sim, we cache the sim, but then this time the cache doesn't get read back into Houdini. Just a reference to it is read into Houdini and written into the IFD. And then when Mantra comes to render it on the right, it's just loading that cache directly. which says a read and a write operation. The advantages are that it cuts the number of read-write operations in half, which dramatically reduces network load, dramatically reduces disk usage because you're not redundantly writing data all over the place, and it makes IFD generation in Houdini almost instantaneous. So you can submit very large sets of renders without having to wait a long time for all those IFDs to get generated. And it doesn't take as long for Mantra to start rendering in many cases. Pack primitives are the current way to do delayed load rendering in Houdini. There was an older format for delayed load rendering, but pack primitives have pretty much supplanted that entirely. They're based on Alembic. They're a generalization of the Alembic format, and they have other advantages besides efficient rendering. They can make working the viewport much faster. If you keep all of your geometry packed, it means that if you have multiple objects that are the same, then you don't need to throw all of that geometry around the viewport. You're just looking at a reference of it. It gives you a good way of handling transforms at the SOP level without having to go to the object level. It's great for instancing, and it's fantastic for RBD simulations. Finally, in the slideshow, I want to talk about different types of pack primitives. There are currently 4 types, and they're all a little bit different. So the first and simplest are in-memory pack prims. These are simply references to geometry data in memory. You can copy them, you can copy them to points and whatever you like, and they duplicate very easily without consuming a lot of memory. So you can have 1,000 objects all sourced from one object. It's much like traditional instancing, but it's a lot better. And you use the pack SOP to create these in Houdini. So then we'll talk about pack fragments quickly. These are kind of really designed for RBD simulations. They're very similar to in-memory pack prims. They're still stored in RAM. And the idea is that you have one master packed object, and then each named piece of geometry is a reference to a part of the whole geometry. You create these by adding a name attribute, a name string attribute to your geometry before you pack it. As I said, they're great for RBD sims. And then we get on to pack disk primitives. These are quite different. You can deal with them in the same way in Houdini, but the big difference is that instead of pointing at a location in memory, they're pointing to a location on disk. Again, they make duplication very fast and lightweight, and Houdini is able to display these at different levels of detail in the viewport. So if you go to your display settings, you can have them turn into boxes once they get a certain distance away from the camera. They're tricky to edit. You need to unpack them to edit them. There's a limited number of things you can do to pack disk primitives without unpacking them. And they're great for rendering. As I explained in earlier slides, Mantra only has to load them as it needs them. You create them by setting your file SOP or whatever node you're using to load geometry. You set that to load them as packed disks. And finally, the fourth type, and the kind of most complex, I guess, is packed disk sequence primitives. So these are very similar to packed disk primitives, but packed disk primitives are limited in that Mantra is only able to access the contents of one of them at a time. So for motion blur, as you've seen from the motion blur lesson, Mantra needs to have access to multiple frames of the geometry in order to create good motion blur. And that's what packed sequence primitives are designed to do. They give Mantra access to multiple frames of a geosequence, and that means it can compute motion blur properly. Now let's look at some examples of rendering and manipulating packed primitives. At the top of our network view, there's an object merge, which is merging the outputs of 6 objects which each contain a piece of high-res scanned rock geometry. These have been loaded from disk as packed primitives, and if I show the node info panel, you'll see. So we have 6 points, 6 primitives, 6 vertices, and 6 packed disks, which are packed disk primitives. So each of these is represented by a point and a primitive. And you can see that the memory being consumed here is very low. It's 16.72 kilobytes. That's because the actual memory that is being referenced is on disk. So it's not, or the actual data that's being referenced is on disk. So this is very light. Okay, I'm coloring them here, and then further down on the left side we have, I'm just unpacking them and repacking them, so that down here we have packed in memory prims, and then here and down here we have a network that's essentially just copy stamping these to a bunch of points. So we've got some points there scattered inside a torus, and down here this is just a kind of fancy way of copy stamping packed primitives. So here we have our in-memory packed prims, and if I show the info panel for that, so now we have 50 points and 50 of everything, including 50 packed geos. Notice that this no longer says packed disk geos, this is just packed geos, so that refers to the fact that these are in memory. And still the memory consumption for this node is very low because it's pointing at packed geometry in memory. Then over here we have packed disk primitives. If we look at this, we'll see that these are still packed disks and the memory consumption is still very low. And again, now we have 50 of these, and these are all still pointing at the same data on disk. Then finally over here I've unpacked all of these, and I've just attribute deleted a color attribute just so that we get the same colors as the rest of them. And if I click on that, it takes a little while to cook, and in fact I'll probably have to fast forward through this when I edit the video. Okay, it's finally cooked. The reason that took so long to cook is because it's had to go through all 50 of these, and it's had to instantiate each of them in memory. If we look at the RAM consumption for that, it's kind of different. So this has gone from a few kilobytes up to 7.36 gigabytes, which is quite a lot. So these are now all full in Houdini geometry. We can select points on here. You see, even this is taking quite a long time because there is a lot of geometry in here. Okay, so next we'll look at rendering these. Here in the object context, I've created a render object for each of these styles of geometry. So we have one for render unpacked, one for a packed disk, and one for packed in memory. And then if I go into the rock context, I've got again one for unpacked, one for packed memory, and one for packed disk. Okay, I've set these ROPs up so that instead of rendering directly, they will save a disk file. Because Houdini has this geometry in memory, it's not a fair comparison of these to render directly from Houdini. So for each of these, we're going to render out a disk file, and then we'll render those from the command line with Mantra, which is worth knowing how to do anyway. Okay, so we'll write out the unpacked example first. So if I hit render to disk, this is taking a little while because it's writing out a cache to disk into our temp directory ifds/storage. We'll take a look at that in a second. Okay, that's done. Then we'll do the packed memory example. And we're writing each of these out to a file that's named for the ROP. Okay, that was a lot faster. And for the packed disk example, almost instantaneous. Now we're looking at the terminal that Houdini was launched from, and I'll just expand that a little bit and clear it. And we can see the three IFDs we've just written out. So they're actually all pretty small. The unpacked example is a little bit bigger, and the other two are the same size. The reason these are all quite small is because as of 2 or 3 major releases ago, Houdini stopped writing data into the IFD files themselves by default, and it wrote them to this IFD directory instead. So let's take a look in there. Okay, so it's written out a BGO file with each of these, for each of these. So one of them, the very large one, is the unpacked one. So this is a cache that contains 2.2 gigabytes worth of data for all of those objects. There's no instancing or replication happening. It's just all of the points and faces for those. The next one will be the memory example. So it's written out essentially one set of the original 6 objects, and then those are just being read in as necessary. So that's a lot smaller. It's 284 meg rather than 2.2 gigs. And then finally, the really small one, which is only 8 kilobytes, that's the disk-packed cache, because that doesn't need to contain any geometry data whatsoever, because it will all be read off disk. So if I look back in my HIP directory, we'll render each of these IFDs. So let's render the unpacked example first. You can do that by typing mantra and doing that. And I'll just expand the terminal so that you can see what's going on. So I set this up to verbose level 2, so it should give us a fair amount of information about progress and about things like time and memory consumption. So right now it's loading all of the data into memory. And by the way, while we're waiting, this is a really good thing to do when you're rendering, actually with any renderer, is just get used to the output, because it gives you a lot of information about what's going on. So now that it's started, the actual render's, not too slow. Okay, that's finished rendering. And the things we want to look at are here. So the total wall clock time is the total time that render took. So that's 1 minute 35.72 seconds. And the peak memory usage is 8.5 gigabytes. Okay, so let's render the next one. And this will be the in-memory prims. Okay, at that render, the wall clock time is 1 minute 24 seconds. And the peak memory usage is 1.99 gigabytes, so significantly less memory usage. Now let's do the last one. Now let's do the last one. Okay, total wall clock time, 1 minute 26 seconds. And the peak memory usage here was 1.76 gigabytes, so that's less again. So certainly in terms of memory usage, the packed disk prim is the most efficient way to go. Now I've actually earlier on. Saved out some of the stats, so we can take a look at them and compare them directly. So as we just saw, the unpacked example, peak memory usage is over 8 gigabytes. It's about 2 gigabytes for the packed memory example, and for the packed disk prims, it's 1.75 gigabytes. Let's look at the total CPU time. It's actually not wildly different. It's a bit larger for the unpacked example. I mean, ultimately, Mantra has to load all of that data off disk, one way or another. So the really big deal for us is the fact that it just takes a lot less RAM to render these things when they're being loaded as raw Houdini geometry. The last topic I want to cover in this lesson is how to get packed primitives to motion blur correctly. What are we trying to achieve? Well, whatever we're rendering, we want to do two things. The first thing is that we want to achieve correct motion blur with as much accuracy as possible. This means that we want center on frame blur, and we want to have as many samples as necessary to represent the motion of the simulation. And then the second thing we want to achieve is this. We want to avoid having Houdini write geometry data into the IFD file or into its IFD caches, so that we aren't doing disk and network read-write operations that we don't absolutely have to. In simple examples like the ones I've been working with here, this wouldn't be a big deal, but when we're working in production, we have to assume that we'll be dealing with very large data sets. To reach the first of these objectives, we need to be able to supply Mantra with usable data at each of the geometry motion samples. For this lesson, I will assume that we'll work with my preferred general purpose settings of 5 samples, from -0.25 to +0.25. Here's a basic RBD sim. I'm copying 6 packed pieces of rubble onto a point cloud, and I'm letting it all drop onto a ground plane. I made a set of low-res proxy pieces for the sim, and then I'm using the transform pieces SOP to transfer the animation onto the original high-res pieces, which you can see there. The sim is running on 8 substeps, which you can see here, to get better collision behavior. At the bottom of the network, I've created a set of file cache nodes, and each one has a separate file node underneath to read the cache back in. On the left, we're writing and reading back in the full-res packed disk primitives, and on the right, we're writing and reading back in the proxy geo, and these are packed fragments. For each type of geometry, we're writing and reading both on integer frames and on subframes. In order to write out subframes, we need a frame number expression that will accurately give us the correct floating point frame number. I'm going to take a short detour at this point and talk a little about Houdini and floating point frame numbers. The traditional way to get a float frame number in Houdini is with the $FF environment variable, but unfortunately this number always gets rounded to 2 decimal places, and then a very long number of long string of zeros or nines gets added to it, and this makes it effectively useless for things like file numbers, because nobody wants files that look like that. So the best way I found to get an accurate floating point value is to multiply the current time in seconds by the current frame rate and add 1 to the result, which is this expression here, and it looks like this. So that's $t times $FPS, and then I'm adding 1 to it in the expression as well, so that it lines up. And that looks a little bit better. So if we do some right padding to this so that all the numbers that have fewer than 3 decimal places end up padded with zeros, then we should end up with the sensible file number. However, I actually did that with this file cache node, and if we look at the resulting frame numbers, we see that we still have these kind of objectionably long and painful frame numbers every few frames. So in the end, what I found is that the easiest way to get these things to line up is to use Python instead. So this is the Python expression that I've ended up using. It's basically exactly the same thing. It's who.time multiplied by who.fps. And then I'm rounding that to 3 decimal places. And I'm adding 1 to it as well. And then I'm using ljust to pad it with zeros. And that gives us a nicely formatted frame number. So now that we have that out of the way, let's look at packdisk primitives first. So we're looking at this netbox here. I'll render the output of the file read for the integer cache. So we're loading a packdisk sequence, and we have the frame range, and then we have the sequence index. Essentially, the PDS is a wrapper on the packdisk primitives cache frames, so they're all available to Mantra at render time, and they can be interpolated to produce motion blur. In order for this to work, we have to set the frame range and index so that the correct files are loaded at the correct frames. This setup might seem a little bit complex, but I believe it's like this so that cached animation can easily be cycled. And this typically has an expression that just takes the frame number and subtracts this start frame. So this is the number of frames between here and here. So I'll go to the ROP, and I'll go to the render view, and I'll hit render. So on the ROP we have 5 geotime samples, but we also have an additional parameter that we need to set under the geometry tab. Now this is one that you'll need to add the way I've shown you before by hitting the little gear wheel icon and the edit parameter interface. This is the packed sequence segments parameter, and when we're interpolating between integer frames, we use this to tell Mantra how many subframes we want to split the interval between frames into. Because we're using 5 samples of motion blur, we're working in eighths of a frame, and that means that we need 8 segments, so we should have this set to 8. And now that this is finished rendering, you can see that it's looking pretty good. In this case, because we've only cached on integer frames, Mantra is interpolating those whole frames, so the blur won't be quite as accurate as if we were catching subframes, but for most cases this will work fine. Okay, now let's look at the subframe cached version. This time we're caching on 0.125 of a frame, and we're just loading it as geometry. Because we're supplying all of the subframes that Mantra needs, we actually don't need to worry about any interpolation, so we don't need to load this as a packed sequence primitive. So I'm just going to flip our switch node so that we're rendering this one. And this will look fairly similar. We just get slightly tighter collisions. Okay, so then we'll shift over to our pack fragments. So the geometry will look different this time because these are just the proxy pieces. So it won't have the same level of detail. So in this case, we are writing out on whole frames. And then we're reading back in again as a packdisk sequence. And we have the same kind of setup here. We have our frame range and our sequence index. So it's doing essentially the same thing. Again, we need our packed sequence segments in order to tell Mantra how finely to subdivide the space between frames. Then finally, I'll switch this to the last one where we're writing out packed fragments. And we're reading in as a packdisk sequence. This is reading in subframes. And again, we'll get slightly better interpolation because it's reading in 8 substeps per frame. Now, if we had to choose which of these setups to use, I would say that ideally writing out subframes with packed disks and then reading them in directly like this is probably the optimal solution, because none of this stuff will get written into the IFD, and that's ideal. I hope that this admittedly rather technical lesson has given you a good grasp of the intricacies of working with packed primitives, as well as their advantages. I'll see you in the next lesson.